Welcome to chapter Heat Conduction and Thermal Expansion. Okay, first we will look into example 12.1. So for example 12.1 we have two properly insulated uniform rods, okay, D and E, make thermal contact at one end as shown in figure 12.7. Okay, the cross-sectional area of both rods are same. The rods are in a steady condition. Okay. So for question A, they wanted to determine the temperature gradient along the rod D, and then number 2, temperature T at the free end of the rod E. And then for question B, they wanted to sketch and label a graph to show the variation of the temperature with distance x along D and also E. Okay. So the thermal conductivity for material D and for material E is given, okay, in the bracket down there. Okay, now let us look into this. Okay, temperature D at one end given 100, okay, and then at the junction DE is given as 80, okay, and then temperature E, okay, let's say the final temperature unknown, we just put it as T, okay, and then the distance x in meter will be 0.2, okay, xd for material D, and then xe will be 0.4. Okay, to determine the temperature gradient, okay, dt over x, okay, will be equivalent to the change in temperature over distance, okay, final temperature minus with the initial temperature. Okay, so since the heat will flow from high temperature to low temperature, okay, so the final temperature will be 80 and the initial temperature will be 100 divided by the distance, okay, so which will end up with temperature gradient of negative 100, okay, Celsius per meter. Okay, and then since the both rods are in a steady condition, okay, so therefore the rate of heat flow will be the same, okay, dq over dt for material D and for material E will be equal, okay, then we can expand the equation. We will end up with the final temperature which will be 20 degree Celsius. Okay, for question B, okay, for the temperature gradient, okay, so from initial point, okay, temperature 100, okay, at 0.2 it becomes 80, and then from there onward at 0.6 it becomes 20, which will be the final temperature. Okay, and 15 degrees Celsius respectively. They wanted to determine, okay, question A, the temperature of the interface between the copper and steel plate. Okay, for question B, the amount of heat flowing from the copper plate to the steel plate in 1 minute. Okay, if the cross-sectional area of both plate is 50 centimeter square and no energy losses to the surrounding. Okay, so over here the thermal conductivity of copper given as 385, and then the thermal conductivity of steel as is given as 50.2. Okay, now let us look into the solution. Okay. Temperature of copper material given 30 degrees Celsius. Okay. Steel 15. Okay. And then the length of copper and steel is given. Okay. Together with the thermal conductivity of the copper and also steel material. Okay. When both rods are in steady condition, okay, therefore the rate of heat flow will be equal. Okay, same. Okay, dq over dt for copper and dq over dt for steel will be equal. So therefore, as we expand the equation, okay, we will end up with this. Okay, and then since we already know the known variable, what we can do is that we can replace in all the values. Okay, remaining which will be the unknown, okay, which will be the temperature in between copper and steel. Okay, so what we need to do is that find out the final value, which will be 29.8 degree Celsius. Okay, further, the cross-sectional area is given as equal. Okay, and then the amount of time given as 60 seconds. Okay, so therefore the amount of heat flowing through the plate, okay, we can determine by substituting value into the rate of heat flow, okay, dq over dt. So replace in all the value, okay, since dt is 60 seconds, we can determine the value of q, okay, which will be 2310 joule. Okay, alright, now let us look into example 12.3. Okay, so this one involves expansion. So a hole in an aluminum plate, okay, has a diameter of 1.178 centimeter at 20 degree Celsius. Okay, the question is that what is the diameter of the hole at 199 degree Celsius, and then B, they wanted to calculate the temperature of the plate when the diameter of the hole is 1.176. Okay, so the linear expansion of the aluminium given, okay, coefficient as 2.4 times 10 to the power of -5. Okay, so the initial diameter is given and initial temperature is given. So what we can do is that we can apply over here into the equation, okay, where the difference in temperature will be final minus with initial 199 minus 23. Okay, so therefore we can calculate the final value, okay, which will be the final diameter, which will be 1.183. Okay, so over here when the temperature increase, we will have expansion lah over here. Okay, so in general when we observe for question B, the diameter becomes smaller. Okay, that means it will shrink lah. Okay, so basically, okay, using the same information, okay, final diameter is given as 1.176, and then they wanted to calculate the final temperature. Okay, using the same equation, okay, we need to determine the final temperature. Okay, initial diameter, which will be the same at 23 degree Celsius, okay, which will be the reference point. So therefore for the final temperature, we will end up with -47.7 degree Celsius. Okay, so basically the diameter decrease or shrink, that means the temperature basically decrease in value for the final temperature. Okay, example 12.4. You have a copper ball, okay, with a radius 1.6 cm, is heated to 353 degrees Celsius. The diameter of the ball has increased by 0.18 mm. Okay, if the coefficient of the volume expansion for the copper is given 51 times 10 to the power of -6 per degree Celsius, they wanted to calculate the initial temperature of the ball. Okay, so deriving all the information given, okay, initial radius given, okay, temperature, final temperature given, okay, and then coefficient of volume expansion is given, and then the change in diameter is given, okay, delta D. Okay, so by using the relationship between coefficient of volume and coefficient of linear, okay, since the coefficient of volume will be equivalent to 3 times coefficient of linear, so what we can do is that the value of the, we can determine the value of the coefficient of linear expansion. Okay, so once you have this, okay, we can determine the initial diameter and then apply into the equation. Okay, so therefore where we will end up with the final answer, okay, which will be 22.1 degree Celsius, okay, which will be the initial temperature of the ball. Okay, for example 12.5, a sheet of aluminium has a circular hole with a diameter of 10 cm. A 9.9 cm long steel is placed inside the hole, which is along the diameter of the hole as shown in figure. Okay, you have aluminium and a steel in the middle. They wanted to determine the change in temperature of the system when the steel rod just touches both sides of the circle. Okay, so the coefficient of linear expansion of steel is given, and for aluminium also given over here. Okay, so when the steel rod just touches both of the circle, okay, so that means the diameter will be equivalent to the length. Okay, so by expanding the equation, okay, what we are going to do is that we are going to determine the change in temperature, which will be equal. Okay, so therefore the change in temperature will be equivalent to negative 83.3 degree Celsius. For the last example, okay, example 12.6, you have a hollow aluminium cylinder, okay, 20 cm deep, has an internal capacity of 2 liter at 20 degree Celsius. Okay, it is completely filled with unknown liquid and then warmed to 80 degree Celsius. Okay, so over here they wanted to determine how much liquid overflow. Okay, so the value given over here, we have coefficient of linear expansion for aluminium and then coefficient of volume expansion for liquid. Okay, for the solution, so the given information is that initial temperature, okay, which will be same, okay, for the container and also for the liquid, okay, and then the final temperature, okay, which will be 80 for the container and also for the liquid, okay, and then the initial volume 2 liter we convert into meter cubic, which will be SI unit. Okay, so this one we have a diagram to show the situation over here. Okay, initially 20 and then we heat it up to 80, so we will have expansion, so the expansion will cause overflow. Okay, the change in volume of the liquid after it is heated. Okay, so we determine this one first, so just replace in the value over here. So the final expansion value, which will be equivalent to 1.08 times 10 to the power of negative 4 meter cubic. Okay, and then the change in volume of the cylinder. Okay, change in the volume of the cylinder, we replace in the value and then we calculate the change in volume, which will be equivalent to 8.64 times 10 to the power of negative 6 meter cubic. Okay, so therefore the volume of the overflow liquid is given, so just calculate the difference lah. Okay, so which will be volume of the liquid minus with the container, so which will end up with 9.94 times 10 to the power of negative 5 meter cubic. Okay, so that's all for this chapter. Have a nice day.